Okay,
Coach,
well,
you can tell
welcome everyone. My name is Travis Kinney, and I have the honor of co-chairing this working group with Jason DeRuber.
You have that
Uh,
listening.
let's see, and yeah, Nancy, are you helping with muting microphones as they come on?
I am. I'm doing my
Thank
best
you.
to keep up.
Much appreciated.
Yep.
It's fantastic with all these folks logging in. Again, this is a live meeting, so you have the ability to unmute. I'd probably encourage you with this many attendees to if you have questions, type it into the chat window. But again, who are we? So we are a subgroup of the National Bridge Preservation Partnership. The partnership as a whole just really has one mission, and it's to spread information on how to preserve and extend the life of your bridges. This working group is specifically a subset that's geared a little bit more towards local agencies. We have a local agency on today to give this training. And what we do is every 2 months, we provide a training opportunity. It's completely free. We're not trying to sell anything. We're just trying to help spread the word on bridge preservation, and it means that you can do it. So again, housekeeping, please mute your microphone. Please go ahead and in the chat window, add any questions that you might have, and we'll try and either grab those at the end, or if there's a good opportunity, I might unmute myself and interject Doug. And with that, I'm going to hand it over to Doug McLain. He is an Oregon representative here. He's Clackamas County. He's a bridge maintenance supervisor with 25 years of experience, and he's going to give us I've actually seen this presentation before. It's a great kind of overview of some scour repairs that you can do actually at the crew level. So I think a lot of these examples he'll show you are repairs that him and his crew have actually installed themselves. So Doug, see you're still muted. We'll go ahead and turn it over to you and take us away.
Okay, hopefully you're seeing a green screen that says AASHTO TSP2 Bridge Preservation.
Yep, we got
Yes,
it, and your audio's good.
Awesome. So a study of U.S. bridge failures from 1980 to 2012, 61 total collapses and 60 partial collapses were caused by scour. Depending on what your job is, some of these topics will be more interesting than others, but these are the ones we're going to discuss today. This failure of the Scour Creek Bridge is what led to the National Scour Program.
Portions of the Scour Bridge continued to fall hours after it initially gave way. The collapse sent cars and a tractor-trailer plunging into the raging floodwaters below. Just how many lives and vehicles were lost remains unknown.
We have one witness that tells us 4 cars, 1 tractor-trailer. We have another witness that tells us 1 tractor-trailer, 1 car. It sounded like lightning struck when the bridge went out. And it just collapsed from there.
Witnesses say it was all over in 15 minutes. The eastbound lane went first. For the drivers of these trucks, it was a very close call.
It cursed me out when it went down.
Plenty of police and rescue crews arrived ready to help, but the waters were moving too quickly, and the risk was too great. All they could do was clear the area of traffic and keep the curious a safe distance away. The governor arrived to survey the damage and watched as still more of the 400-foot span came tumbling down.
We don't know exactly what caused the collapse of the span. We're going to be very cautious about this. And any bridge that the state police see, or the Department of Transportation, or the Thruway see, that they regard as something to be avoided for the time being, we're going to avoid it. Now, there'll be a lot of unhappy people, and there'll be a lot of detours, but so be it.
All of the other bridges along Scour Creek were closed since 6 a.m., including this one at Mill Point, which appears ready to give. Residents here want to know why this bridge wasn't also closed down.
If there was any thought whatsoever that this bridge was in danger, this road would have been closed.
So there's a little more of that video, but it pretty much shows you what happened there. The National Transportation Safety Board figured this out, and the 2 terms that we should be paying attention to here are scour and spread footings. That accident on Scour Creek is what caused the National Transportation people to figure out that we needed to start inspecting for scour. So owners of bridges are now required by regulation to develop certain plans, all of these things. In Oregon, were fostered by the Oregon State Department of Transportation. They really help the local agencies work through these requirements. The Scour critical definition is here on the screen. The NBI coding guide item 13, it uses numbers and letters to code scour vulnerability, and we'll go over those. So the U for bridges with unknown foundations, we have to consider those scour critical because we're not sure whether they are spread footings or pile. We just don't know. So they're going to be treated as scour critical. We don't worry too much about structures with a 9, 8, or 7. Sixes should be monitored because we don't know what their vulnerability is. And 4s have been identified as something that could use some form of mitigation, but hasn't been done yet. Now here's a couple that are in the scour critical coding. 3s and 2s need to be monitored during high water events, and they're calling for current mitigation on all 2s. They've already located some problems with those that should be taken care of. Hopefully none of us will see 1s or 0s. A 0 pretty much is a bridge in the water. We just looked at that for Scour Creek. We'll go over some of the terminology. So the 4 types of footings on the left of this sketch are all showing a deep type of footing that is somewhat resistant to scour. Yes, eventually scour can affect those. Usually it has to have so much removed that they're not going to have a catastrophic failure. The spread footing on the right, however, that's what was at Scour Creek, and that's the ones we're particularly worried about because it won't take much undermining before that bridge becomes unstable. So this is a picture of aggradation. Aggradation is the buildup of materials, usually in places that we don't want it. In this particular case, we've got a gravel bar forming where the channel should be. This is degradation, and that is the removal of materials, again, usually in places where we don't want it. This happened at an abutment on one of Clackamas County bridges. It didn't adversely affect the bridge because the pile tips were deep enough, but it washed away the abutment to where eventually there was just a patch of asphalt going over the gap between the remaining abutment and the bridge. This can also be considered local scour. Local scour is something that happens on an object in the waterway. Lateral stream migration. This is the same bridge we just looked at, and this is what caused it. Originally, when this bridge was built, and this wasn't a very old bridge when this happened, the channel went right down through the center of the bridge, but eventually we had an aggradation pile build up, and the river decided to reroute itself to the right, and by moving the velocity over there, that's what ate that abutment away. Excuse me. Angle of attack. That's essentially the angle that the water is actually hitting the structure. Ideally, that water is going to come parallel to the abutments and run straight through. This bridge, you can see, has a pretty steep angle, and I'm not sure what you can see in the picture, but if you look real close, you can probably see armoring on the left abutment there, probably some big boulders, and you can see how the current has scoured out a deep hole on the left side of it, but actually left an aggradation pile on the right. Angle of attack is pretty important, whether it's a big bridge or a small bridge. It's one of the things we try and deal with when we're doing mitigation. A plan of action. So all critical bridges, scour critical bridges need a plan of action. They include a lot of information, but essentially they're there to tell us what to do in high waters, how we mitigate things, pretty much everything to do with scour on that particular structure. and they are a requirement for all scour critical bridges. Again, ODOT, Oregon Department of Transportation, helped us with these plans of actions. Here's all the information that's in a plan of action. It's pretty detailed. Some of it's more important than others, and depending on what your job is, it will change what's important to you. So this one is probably the most important part. What type of footing is it? This one, we can see it's spread footings poured on bedrock. Who's responsible for the plan of action? What is the scour vulnerability? The scour evaluation summary that's highlighted there, that's the current condition of the bridge. You can see below there's some history, but the current condition is what we're really interested in, and that's the information that we need to take with us when we're going to the field to do high water inspections. So this is what we should be doing and what we have done. Recommended actions. Here's the coding information. You can see highlighted, we are scour critical at a 3. If you look over to the right, you'll notice that at one time it had a 2. Now this, we didn't change from a 2 to a 3 in this particular case because of any form of mitigation. What changed it was some more investigation. We realized that it was sitting on a relatively solid foundation of bedrock that wasn't going to erode anytime soon. So we were able to move it from a 2 to a 3. So in the monitoring program, the important thing is what is it that we're looking for? In this case, we want to make sure that the spread footings aren't undermined. So this is further monitoring information. How are we going to inspect? When are we going to start? In this case, it says bank full. What stage of the river level do we go? And how often do we monitor it? Well, the how often is going to change with every event. There's times that we can go up and look at a bridge and the water level, maybe it just hit bank full, and there's not a lot of problems there that we can see. Everything looks good. We might not go back for 12 hours, 24 hours. But there are times that we've gone up and looked at bridges where we don't leave that bridge as soon as we get there. A good example was that one that we looked at where the road, the abutment got, or excuse me, the approach got undermined. As soon as we got our inspector there, they didn't leave. Countermeasure recommendations. This is for that same bridge. It's sitting on bedrock. There wasn't much we could do to improve it. So there's nothing in there about what we were going to do to fix it. This is a continuation of countermeasures. And then there should be some detail about what would require us to close this structure. You can see the highlighted areas, observed structure, debris accumulation, loss of road embankment. Those are the 3 things that we've identified in this particular bridge that would say we're going to close it. Detour routes. This was on a dead-end road, so we didn't have one. But if you did, this is where the detail for that detour route is going to be filled out. And there should be a document in your attachments showing that detail route. You can see the check marks here. This one actually says it's supposed to have a map showing the detail route, but I guess our POAs need a little bit of work. Okay, the actual inspections. NOAA has stream flow gauges on most major waterways. Most of them show what the levels have been and what the prediction is for the next few days. Those gauges are what we watch to determine when we start monitoring. We start monitoring at action stage on this chart here. An action stage can be considered the same as bank full. And we will continue to monitor those structures until it leaves action stage. Now, this is a copy of one of the documents that we would take with us into the field for inspections. It's sorted by drainage and sub-drainage and identifies the affected areas of the foundation, what type of foundation, and any history that we could put in there that might be pertinent. This is a close-up of the most important part of that document. You can see the scour code rating, the affected areas, and what type of footing. Most of our sub-drainages, even the ones that have gauges, aren't going to have anything that predicts what the flow is going to be for the next few days. So we try and look at all of the sub drainages whenever we go out and look at the major drainages. If the sub drainages aren't affected because the major drainage is reacting to snow melt, maybe we won't go back the next time and look at the smaller drainages. But everything in the main drainage, if that NOAA prediction says we're going to bank full or action stage, we'll go out and look at all those drainages at least once. So what do we look for when we get there? Obviously, we should all know at this point not to drive through water. We have had fatalities in Clackamas County where we had an overtopping of a bridge and somebody did try and drive across it and it cost them their lives. So pressure flow at the low bridge. It does say pressure. So if we've got essentially a pond where the water's backed up and it's covering the lower chord of a structure, that's not nearly as concerning as if it's in a streamway where you got velocities pushing against it. Most of these structures, modern ones, are a little bit different because of seismic, but most of the older structures really don't have any type of reinforcement for horizontal pressures. So when you start seeing water flows against the lower chord, it's time to consider closing. Vertical or lateral displacement. So how do we know if something's moved? One of the best ways is to look at the guardrail or the barriers. Most of the time that bridge has a barrier of some kind that goes across the bridge and is attached to the approaches on each side. If the bridge moves, you're going to see a wow in that guardrail, up, down, right, or left. So that's a really good indication if you've had some movement. The other thing you could look at is a misaligning of the road striping. If you come up to a structure and the stripes don't line up, there's a chance that superstructure is moved. Excessive horizontal vertical separation. Okay, that you're probably going to look for the same things that you'd look for vertical or lateral displacement of the superstructure. If the joints are out of whack, it's because the superstructure essentially moved. You may notice a place if you had rotation one way or the other, maybe things, the guardrails or the barriers wouldn't have shown it, but you could go up and look and, hey, that joint used to be 2 inches wide and now it's 6. Well, you probably had some kind of rotation there if that happens. The problem with damage is sometimes that damage is already there, but that helps if you know what your structures are. The question you got to ask is the damage I'm looking at new. Sinkholes and roadway. Don't forget we had that problem where we lost all of the fill under the roadway, but we didn't have a sinkhole, but all we had was a piece of asphalt, which wouldn't support much. And debris buildup. Debris buildup isn't really scour, but when we do high water inspections, we're looking for that as well. A big pile of debris can put a lot of stress on that bridge and give you that horizontal pressure that you're trying to avoid. This is a picture of some fairly substantial debris. This one, actually, this is the one that caused the death, the fatality. This thing caused overtopping of the bridge eventually, and that's where the car went off. And it also caused some damage to the bridge. Those 2 bars that you're seeing running away from you, those are 9 bars. That's 1 1/8 inch in diameter. And that log hit it hard enough to pop out all that concrete and bend those reinforcing bars. So what do we do post-event? Well, a lot of what you're going to read in some of these plans say, hey, we want to go 24 hours after the event and go check these footings. Well, sometimes that water might not drop down for a month, but it is important as soon as we can to get out there and actually do some probing to make sure we don't have undermining on any of these spread footings. And really the only way to do it is like you're seeing in the picture, by hand, or in the areas that you can't actually walk to, we'll get a diver out there and they'll put their eyes on it. In our case, all the diving is done by our state agency, and they will take a look at these on a regular basis. and give us reports. If we had a situation where we thought there was some scour and we couldn't get to it, we can call up the state and say, hey, we think there's a problem there. They'd send somebody out to dive on it. So we can look at some failures here. These are all Oregon. This is over east side. This is a spread footing bridge that just completely disappeared in a high water event. Undermining caused the spans to disappear. Another Eastern Oregon bridge. You may be able to see in this photo how the deck at the barriers is sloping down on the far side. That's where the spread footing was failing and sinking on the other side. Same county, same event. The bridge, in fact, stayed put, but it lost its abutment. This red line is actually the end of the bridge and shows you where the abutment was attached before the event. These guys over in Umatilla County got hit pretty hard on this one. This is actually a pile bent that sunk. The pile tips weren't deep enough to prevent scour. Here's another view of it, looking at it from the other direction. You can see how that left end of the span is dropping down. That's where the piles failed. And this is Tillamook County down on the coast. The abutment washed out and the whole abutment and first span disappeared. So how do we prevent it? Here's a simple bridge where, if you look, that is the concrete cap, and it was starting to lose its fill material underneath. We figured a few years from now, maybe it would work back and get underneath the approach. So we thought we should just put some simple armoring in there. There wasn't a lot of velocity to worry about, but we just put armoring along the bank, and it has prevented the erosion. Here's another simple erosion problem. This is a downstream wing wall on a fairly mountainous river. It's sandy bottom, a lot of erosion up there. We essentially just put armoring along the area. We didn't worry about protecting the armoring itself because it was protected by the wing wall. The velocities weren't going to be terribly high in that corner. That's held up pretty well. If you do have to worry about higher velocities, sometimes they'll tow in the riprap wall like this drawing shows. Sometimes this is referred to as a golf club design. The head of the golf club is full of riprap, and it helps that armoring stay in place. The riprap head is actually buried well below the stream bed. This is also that same bridge we looked at where the abutment disappeared and the piles were exposed. Had lateral stream migration. The solid line with the triangles is the original profile of the stream bed, and you can see how the original channel was in the middle. The dashed line shows what happened after the event. The middle filled up and it pushed the stream over to the right. This is a before picture of a small bridge we did a mitigation project on. It had a bad approach angle and it was coming in pretty fast and was eroding the abutment on the far side. I'm not sure if you can see in the picture, but you're looking at the top of an exposed footing over there. It was also eroding the near wing wall. It made the big aggradation pile that you can see right there with the tree growing out of it. So this was our plan here. You can see the water, the stream flow is from the bottom to the top. The blue is showing the existing water at the start of the project. The hashed area is the aggradation that we were going to excavate out. And the red is porous rock wears and armoring. Those porous rock wears are a series of rocks that angle upstream, and they force the water to make little eddies above them, and it helps not only fill in the area above them, but it directs the current away from the wear. This is what a porous rock wear looks like before it's been covered. Typically, when we're done placing those rocks, we'll cover them with what we call river run. River run is simply a pit run rock that comes out of a quarry that's built on a stream bed, and it's made out of big round rock, small round rock, and sandy gravels. And once you wash that all in, it looks pretty much like the original stream bed. You can see with this porous rock wear, the biggest rocks, the tallest rocks are at the right. It's angling upstream. And as you get close to the center of the stream, the height of the rock gets lower. So to do this particular job, we had to de-water the site because we were going to put an excavator in there. To de-water the site, we had to put a cofferdam in with a fish net. We pumped around it with a couple of pumps. One's a backup, one's primary. And then the water was pumped through the site into a diffuser downstream. And the idea of a diffuser is to keep silt from building up. Sometimes, depending on your location, you're going to be required to put a downstream cofferdam and fish net in as well, because the slope is such that the water could back up into your excavation. The big challenge with this type of work is keeping the turbidity down. We don't want muddy water going back into the creek. This is a mitigation plan. This is what we were going to do when it was over. Hopefully that blue line is where the new creek channel is going to be. And all the little hash marks and X's and dashes, those are what we're going to put back in as far as vegetation. So here's the before picture. And this is one winter later. You can see part of the porous rock porous rock barb coming out there, forcing the creek over to the center. You can still see the exposed footing. This was a pretty narrow bridge. There wasn't much we could do to protect or rebury the footings, but it did take care of our erosion problem on the right, and the footing was no longer in danger of being undermined. This is a concrete floor bridge. The slide you're looking at now shows you the edge of the bridge. The part on the left shows you an undermined area where the scour hole had actually worked its way under this concrete floor. This is the downstream end. You can also see where there's a scour hole at the bottom end where the flow was coming off of that concrete. So here's our repair plan. The flow is from right to left. We intended to fill the scour hole at the upstream end with boulders and river run, making sure that we got all of that fill material underneath the undermined area. The downstream end, we not only filled with boulders and river run, but we built what's called a full spanning porous rock wear. This is an example. I think this is that actual bridge where we installed a porous rock wear. It's essentially the same as one of the barbs that comes out. The lowest point's in the middle. It's angled upstream, but it spans from one side of the waterway to the other. When buried with river run, it fills up and looks just like the bottom should be. Here's an after picture. You can see how the gravels are up on top of the concrete now. And this is the downstream end. You can see the center of that rock wear. And you can also see that there's gravels upstream of that. So here's another bridge that had a multitude of problems, bad angle of attack, aggradation, degradation. The channel essentially is pushing at the abutment on the right. We wanted to put it back towards the center. So here's the plan. The flow is from the bottom to the top. We decided to install a porous rock wear up at the top of the bridge, excavate all of the hashed area showing aggradation, and then we were going to armor the one bank that was getting undermined from the flow. This is one of the ways that we armor an abutment. You can see on the left side there are a row of boulders. Depending on how much room you have to work with in the situation, there could be 1, 2, 3 rows of boulders there, and then we'll cover it with river run. Now that looks like a really dirty pile right there, but again, when it's washed in, it looks pretty much just like a normal stream bed. There's your before, and there's your after. We saw this one earlier in the example of aggradation. We wanted to put the channel back in the center of this structure. So here's our repair plan. We have the flow going from right to left. The idea was to cut out all the aggradation at the downstream corner there and in between the centers and armor both banks. There's a before, and there's our after. Now those stream bed materials you're looking at on both sides of the creek in the front of that photograph and the lower end of it, those were placed there by us. That's what River Run looks like after the water's had a chance to play with it for a while. So this particular structure, the creek bottom had disappeared probably a couple feet over the years and exposed a water line, an abandoned water line that was covered with concrete. What that did was cause the water to flow around the concrete, and it was starting to erode the bank on the far side, as well as it was kind of an impediment to fish travel or fish passage. So our plan was to remove the pipe and the concrete, create a couple of full spanning porous rock weirs, and cover them all with boulders and river run. Here's our before. There's our after. Again, if you look at the far bank going up along the pipe, you can see what river run looks like after it's had a chance to wash in. This structure had migration over to the right side. The creek should be running right down this center bent that we're looking at, but it had migrated over to the far side. If you can see it, it's starting to undermine the timber back wall there a little bit. So our thought here was move it back to the center as best we could. Here's our plan. The flows from bottom to the top. We were going to install a porous rock weir at the top to deflect the creek back towards the center and armor both sides. Also excavate the aggradation. One thing I'll mention about excavating aggradation here, if we're in a spot where the stuff we're digging out looks like good material, we'll stockpile it and put it right back where it came from. If it's silty or clay or something that we don't want back in, then we'll get rid of it and replace it with something else. But we will reuse the native soils wherever we can. So here's our before and here's our after. So during this project, we determined that with the angle of attack that was coming in, there was absolutely no way that we were ever going to be concerned with the left abutment being undermined. So we actually didn't dig all the way down and armor that side. We dug a lot of the aggradation out and got rid of all the silty materials and covered it back up with some river run. And it hasn't eroded at all since then. Here's one where you got a bad angle of attack, degradation on the left, aggradation on the right. It was undermining behind the wing wall and this footing on our left. And this is actually a two-span bridge. And where it was coming in, it was hitting the middle bent and undermining that bent as well. So the flow is from left to right on this one. Here's our repair plan. You notice we not only had a couple barbs at the top of the wing wall, but we went upstream quite a ways and put a barb in there trying to get it away from that side. We moved it a few feet. We weren't able to get it back in the center or change the angle of attack, but we did get it away from that wing wall to where it wasn't eroding anymore. The other thing this plan shows, is armoring of the center bent, which was completed. So there's the before and there's the after. Again, you can see we didn't change the angle of attack much, but we were able to move it over away from that wing wall. There's a few other methods here. This is one we installed. This is called core rolls, and it's a roll full of some kind of fiber. I'm not sure if these were coconut or what, but they're fiber rolls, and you can stake them in, and they will take vegetation really well. This one's probably been installed 3 or 4 years. The picture on the left, It's probably been there 3 or 4 years, and it's really part of the bank now. This is a picture of revegetation for stabilizing the bank. They didn't do anything other than put willow and other woody material in there. On this side of the mountains, we typically use dogwood and willows for our stakes, and they grow really well. There's a lot of different mitigation methods out there. One of the things we have to be concerned with over here is the Endangered Species Act. We've got endangered salmon and steelhead and lampreys. So we have to be real careful with our water quality, with how we treat our fish, and our mitigation methods are kind of controlled by that. This probably was Clackamas County's big first dewatering type of repair. This is showing the south abutment, and there was a section divers found, ODOT divers found that was undermined. And there was also a problem on the north abutment. Now, this is a spread footing, so we were real concerned that it was going to lose its support. Here's the bottom right shows a close-up of the repair plan. We essentially went in and dug a trench 3 feet below the existing footing and filled it up with concrete. When we did that, we not only filled up the void, but we made the scour have to go 3 feet lower before it could get under the footing. But to do that work, we had to dewater. So our method was using plastic sheeting and sandbags. To get them under the bridge, we hung a beam with an electric trolley, and we were able to place all of our sandbags under the bridge. This is our completed cofferdam. We don't use this type of pump anymore, but we do always use a fish basket. That's a screen that means we won't be sucking up baby fish. So we started a dewatering process. Once we start dewatering, the next thing is to remove all of our fish. At this time, we had a fish and game guy that worked with us, and we would go in and shock the fish. Typically, it might take us 3 or 4 passes as the water is receding and pools create to try and remove all the fish. Fortunately, we now can do our own shocking. We've had some guys pass the training class, but even at this time, depending on the circumstances, it may take you several passes to get them all out. So this is after we've done most of the draining. If you look at the right side of the photo next to the sandbag wall, you might see ripples in that water right there, and that's because that's flowing water coming in through our cofferdam. We had a really tough time stopping water because this is a cobble bottom and cobble leaks. So the first thing we tried is more sandbags, a lot more sandbags, but that didn't work either. So eventually one of our guys figured this one out. If we stretch our plastic upstream, we can tow the plastic down, and it prevents the water from going into that cobble there. If you look at the close-up on the right, you might see that plastic looks like it might have been vacuum packed to the bottom. That's the water pressure trying to shove through that cobble. There's a few things about this method that you have to be careful of. You got to make sure that there's nothing that'll poke through your material between the cofferdam wall and the toe of that plastic. And if you look real careful in the picture on the left, you might even be able to see a little difference in the color between where the row of sandbags in and the stream bed 3 or 4 feet upstream. That's because we removed all the big rocks and all the debris. So when we put that toe of plastic down, it was smooth bottom, and we sealed it as best we could. It's the way we do all of them now, and it works really well. The farther up you can put that plastic, the less leakage you're going to have. So once we finally got the water in control, we brought in our excavator, and we started removing our temporary repair panels. So when we first found this hole and we weren't able to go in and do this job, we didn't want it to get any worse. So we manufactured these panels out of plate and flat bar, and we just drove them into the stream bed with a 60-pound hammer. That prevented the scour from getting any worse while we were waiting. One interesting note was before we got approval to do this, ODFW, our Fish and Wildlife people, had us cut holes in the panel wherever it was going over a void so that fish wouldn't be trapped. So we're coming down to the end of one trench on that side. We're dumping into these 3 cubic yard sandbags because the stuff we were digging out of there was not suitable to put back. I mentioned earlier that we try and reuse our material. This is not the type of material that we would have wanted to put back. So here we are checking our trench, making sure that we're at depth. This is showing where the edge of the void was as we're digging up. You can kind of see it's a clayey silt. Pretty hard to dig with a shovel, but as far as erodible materials, it's definitely eroded. So we cofferdammed around this site, and most of the water stayed clean, but the water that was flowing into our excavation had to be pumped out. Now, that water that's coming out is going to be silty and dirty, and we needed to filter that out. So we created this big filter area between using hay bales and filter bags and this diffuser that actually had a little tube of flocculant in it to help the silt drop out. We were able to filter our water to where it didn't run back into the creek dirty. Over the years, we found that the best way of filtering water is pump it through the land. One of the first things we do on a scour project is try and find somewhere to pump our dirty water to where it'll be contained and eventually have to filter through the ground before it gets back in. If we have an area where we can't do that, then we'll do something more substantial like the hay bales and filter bags. But typically the best way of filtering water is to find some place where it'll just pool up and naturally go through the soil. So this is after we're done trenching. You can see some cobble has worked its way back in there. When we got the cobble out, we realized it was a pretty substantial hole. So here's where we're starting to pour our concrete in. We talked about the dirty water coming out of an excavation from digging. When you have dirty water that's being forced out of an excavation from concrete, it definitely needs to go through a filter bag and go into an area where there's absolutely no way that concrete water can get into the creek. It's really important that stuff doesn't get in because it's very hazardous to fish. So we always use filter bags whenever we're pumping water that has been exposed to concrete. Here we're covering up the excavation with river rock. Kind of hard to see, but there's finished product. Here's one where I got a call from Rick Shorb, the old retired ODOT diver. He said, "You guys have a problem." And the problem was we had some fairly substantial undermining under a fairly substantial structure, and it was right under one of the main columns. This was holding up a pretty good sized deck truss bridge, and that undermining you see is, right under one of the main columns. This is a picture of the area that the undermining was in. The corner of that footing and the round column coming up on the right of the picture is where the undermining was. But when we first went down there and looked at it, we realized, well, man, all those rocks down there with the moss on them, they obviously haven't gone anywhere in a long time. So we didn't want to go destabilize the stuff that was obviously still staying in place. And we made a plan to just place rocks in the areas that were missing them. To do that, we had to measure and sort and find the exact right rocks that were going to fit. This was a fairly good drop down to the river from the deck. There was some concern that the weight of the outriggers was going to punch through the deck. So we made sure that when we deployed this thing, we went right over one of the bents or one of the transverse beams in there for support. So we weren't just right over a deck with nothing underneath it. This is what the footing looked like when we started a project. One of the issues we figured out was, hey, if we want to put these rocks in particular places and we only have the ability to drop them in, if we put a sling around them, when we go to roll the sling off, the rock's going to move. So we came up with a method which was drilling holes and using anchors to where we could place the rocks just the way we wanted them and then remove the anchor and the rock wouldn't roll. The guys spent quite a bit of time sorting rocks and making sure we had the right ones. And they actually went as far as to drill them ahead of time and stage them in the back of the truck to where they came off in order. This is a picture of us actually placing rocks. You can see we hung a beam to move them underneath. And rather than using that electric hoist, the guy said it was my decision to use the chain hoist rather than the electric hoist. I don't remember doing that, but they did remind me of that quite often as they got pretty tired of using that chain hoist. You might also notice we put that beam at a little bit of an angle. It definitely helped going downstream, but if you overshot, it was a real pain. So once we got our boulders in place, we wanted to cover it with river run, and the way we figured out how to do that was cubic yard sandbags. We'd get them over the position we wanted to use or to dump them, and then we just cut the bottoms out of them. So there's a before and an after. Now, ideally, you'd probably say there should be some fines over the top of the exposed boulders, but there's a lot of velocity going through there, and we weren't able to maintain any of the smaller rock. But if you look real close between the boulders and the concrete footing, you're going to see gravels and small rocks in there. Those boulders have held that material in place on the inside, so we feel that it was very good repair. So Still Creek Bridge, this is one of the latest ones we did. Before my time here, there was some undermining on this abutment, and they went in and simply poured concrete over the boulders and the undermined area to protect the bridge. Well, 20, 30 years later, probably 30 years later or more, we found that there was some undermining not only under the overpour, but we could poke our way back in there and realize it was going under the bridge. How much under the bridge, we couldn't tell until we removed the overpour. The picture on the right shows where we were starting to break the overpour out. And right next to that stick, you can see where there's undermining under the footing. One of the things we didn't know when we tore into that was that this bridge was actually sitting on piles. So if the undermining kept going, would the bridge have failed? Probably not, but we would have started losing fill on the approach. So even though we found piles in the bridge, it was still a good repair, and it was something that needed to be done. Unfortunately, a lot of the structures we have, we just don't have plans for. So here's a plan of how we were going to repair it. We're going to precast concrete panels and bolt them to the abutment. We are going to dig down deep enough below the existing grade that we weren't worried about the creek bed undermining the concrete panels that we were putting in. We anchored these panels probably 4 inches off of the abutment, so we had room to pump grout behind them when we were done. So they were secured with bolts and filled with grout. Once we were all done, we armored that front with boulders and river run. This is a plan view of the project. And this is a picture of the completed project. There's the bolted panels, and below it you can see where the top of the gravels and the concrete, the top of the gravels over the boulders are showing you the armoring. Okay, that was all I had.
Doug, that was fantastic. Thank you. We do have a few questions that I'm going to start peppering you with, if you don't mind.
No.
So on that salmon river repair, did you guys end up putting some flowable grout underneath the footing on that one?
We did not.
Did not?
No, the concern there was the dewatering, because if we put grout in there, we would have had to completely separate the work zone from the water. And the engineers felt like the undermining wasn't bad enough that we needed to put that in there. So they were happy with just stopping any further erosion.
Oh, perfect, perfect. And then, yeah, I guess that was one of my questions. You showed a lot of different plans for different repairs. Is that something that the maintenance crews are developing with your knowledge, or are you looking for outside resources? Who puts those plans together?
So in our case, we have a guy up in engineering that's our permitting guy, and we work together with him when we come up with a plan. We go out, identify what it is that we're going to do, figure out how we're going to do it, and between the two of us, between maintenance and our permitting guy, we come up with a plan. Occasionally, we had a job that isn't in this presentation where we had to work along ODOT asset right along one of their state highways. Well, once we got them involved, then we were required to go out and hire actual hydrologists and engineers, and it got pretty involved with everybody that had to be involved in that project. But normally, it's just a team of maintenance and our permitting people on top of the hill.
And I'll start this comment by saying my apologies to my hydraulic engineers on the line, but I've had similar experiences where when you design the repair for the max flood event, jetty rock ends up being an answer for a lot of the streams that I've been involved with. And I think at times it discourages maintenance from doing what I would call more of a maintenance repair. So that kind of leads me into another question, which is when you would do these installations, I saw you had on, at least on Salmon River, you mentioned going back and kind of observing and looking at the how it's performing. Do you guys do or plan for ongoing maintenance of some of these repairs?
We do follow-ups. Part of it's actually required by our permits to go back and review and make sure vegetation's working like it's supposed to. But yeah, we typically will go back and look at all of these sites. We do an annual inspection of all of our structures every year. So we get a chance to look at them and see how they're performing. As far as scheduled specifically to go back and look, once the permitting requirements have been tackled, we don't have anything scheduled to actually go back and look at that particular project.
Okay, perfect. And so you already covered this a little bit, but you have in-house permitting resources. Can you give us a little bit more of a context into the permit process? I suspect a lot of folks on the line will shy away from this work because it's like, look, like by the time I deal with all the environmentalists, this is going to be 3 years from now.
Well, I can't say that it's terribly difficult because I'm not the one that does it. But I think our permitting guy, after the first couple of years, has a pretty good handle on it, and I don't see that there's a lot of stress involved. In our area, we're dealing with I think 5 different agencies that have to approve what we do. I think the Department of State Lands, Department of Environmental Quality, Corps of Engineers, Fish and Wildlife, and it seems like there is a 5th one, but I can't remember what it is. But this is a multi-agency application. It's not overly complicated once you figure out how to do it. The one thing that you do have to be aware of is it's very time consuming. I'm not going to get a permit. If I started right now, I don't think I'd have a permit for work next summer. You better be planning 2 years ahead with the permitting process.
Yeah, and the only thing I'll tag on to that is unless there's an emergency declaration and then you kind of bring the regulators and do the work along the same time, then my experience has been then you kind of file for the permit after the work is done. But that's only when I've had an emergency declaration. So for some of you that are kind of thinking through that environmental piece, I'll be surprised if there's many other areas of the country that have to do more hoops than Oregon. But so encourage you to get started with that.
We have done projects differently than we would if we had had a permit to try and avoid permitting because we knew that this was going to be a challenge and slow us down. So if we can get around it by doing work a different way, occasionally we'll do that. But I don't think anybody here is afraid of the permitting process. It's just something that has to be done, and we're actually pretty good at it. And as long as you plan far enough ahead, it really isn't a problem.
Let's see. So I got a question here regarding the check dams that you guys have built, and it's do they trap a lot of sediment? And if so, do you need to actually like remove the sediment?
No, we actually, in most permits, it's not like we can't have any turbidity, um, but you have to limit it to certain periods of time. Like if you're turbid over a certain amount of time during the day, you shut the project down. There's certain levels. We check every 2 hours. We actually go out and take water samples, and there's turbidity monitors that'll tell you how much difference it is from upstream of your job to downstream. Um, but we've never had a problem with pulling dams. Yeah, you're going to create some turbidity for a short period of time, but there's very few places that we've worked that turbidity, if it's just clearing your cofferdam or having water run through your work site after you've completed your work, that drops out really quickly. And I don't think we've ever had a violation of a permit doing that.
Yeah, and the way I read this question is less from an environmental standpoint, but it's more of like a long-term and I think, unless I'm off of this, I think the check dams, the purpose is to create aggregation in that area, right? Like it kind of traps some of the sediment long-term and forces the stream elsewhere.
Are you talking about the like full spanning porous rock wearers? Not our cofferdam type?
I'm not sure.
Yeah,
Jason, if you're on the line still, you might you can shoot us a clarification on that one.
Yeah, I don't think I've even used the term check dam in this presentation. I'm not exactly sure what he's talking about.
Yeah, I think it's the weirs probably.
So the porous rock wears are only going to hold fine material up to the top of the coarse material, and the current just washes everything out, and it looks just like stream bed everywhere else. The deal is you're just raising the bottom of the creek up, and then it's just going to look like normal creek bottom. Whatever's upstream from it and whatever's downstream of it is just going to return to its natural state. It's just going to be a little higher.
Okay, I think we have time for just one more here. I got a question about okay, let's do this beam trolley because it is very creative. I love watching how maintenance gets things into place. So regarding that, the steel beam trolley, what is the best way to get that beam into place under the bridge? And have you used it on bridges that aren't steel beam girders? So the ones that have a concrete beams underneath, can you still use it there?
Yeah, so we always use a crane to get it under, and typically you're only going to be able to get half of it underneath with the crane, and then you'll have to grab it from the other side and drag it through. Sometimes, depending on what's going on the ground, we may end up, we've put them on floats before where we grabbed one end with the crane, the one we had to pull upstream, and the back end was sitting on floats. Every situation can be a little different, but typically we're going to set it down from one side and then pull it all the way through from the other. What was the second part of the question?
It was, do you have to have steel beams underneath it, or can you sling it off of concrete girders too?
The Salmon River Bridge, we actually suspended that from a concrete parapet.
Okay.
So we typically will hang it off whatever's there. The Meadowbrook Bridge, we actually bought special clamps where we could clamp the beam to the bottom girders. But we can hang it with chains off of concrete, whatever you can grab. It's pretty flexible as far as the way you can get them installed.
And that'll just reiterate that I have always said maintenance crews are worth their weight in gold. Okay, so we are at time. In the chat window there, folks, I just put a link to the TSP2 website. If you're not familiar with our group, that's where you can find some of our a ton of information, both roadway and bridge stuff. Feel free to explore around. Earlier in the chat, I put a link to the video library, and I'll type that in here again just to get it at the bottom. But that's where this video will be this was recorded. It'll be posted online, and I don't know, usually takes a week or so. And then if you have, we'll do another training in January. We take December off. We do it every other month. And so if you have any ideas for trainings that you would like to see, shoot me an email. I put my email in the chat there as well, when we can find hopefully another great presenter like Doug to provide the whatever topics you're looking for. With that, I'm going to go ahead and release everybody. And just one more time, thank you so much, Doug. This was fantastic. Everyone give your virtual clap for Doug here.
My pleasure. I hope it was good for everybody.
We